Welcome! In this session, we'll be diving into the problem titled Rings and Rods. This problem challenges us to work with string manipulation and logical reasoning to determine how rings are distributed across rods. Let's explore the problem, break it down step by step, and craft an efficient solution. Stay tuned! In this problem, you are given multiple rods and rings, and your goal is to determine how many rods have all three types of rings: red, green, and blue. The rings are represented in a string called rings, where every two characters describe a ring and its corresponding rod. The first character in each pair indicates the ring's color, R4 red, G4 green, and B4 blue, while the second character indicates the rod number, ranging from 0 to 9, where the ring is placed. A rod is considered complete if it has at least one ring of each color, red, green, and blue. Your task is to analyze the string and return the count of rods that meet this condition. The input string will always have an even length, and there can be up to 50 pairs of rings and rods. The output of the problem is an integer representing the number of rods that contain at least one red, one green, and one blue ring. Let's look at the examples to clarify. In the first example, the input string rings is B0 R0 G0 R9 G9 B9. Here, rod 0 has the rings B0, R0, and G0, which means it contains all three colors. Similarly, rod 9 has the rings R9, G9, and B9, also making it complete. Therefore, there are two complete rods, and the output is 1. This demonstrates how to identify and count rods that satisfy the condition. Now, consider the second example where the input string is B0 R0 G0 B1 R1 G1 R2 G2. In this case, rod 0 has B0, R0, and G0, so it has all three colors. Rod 1 has B1, R1, and G1, making it complete as well. However, rod 2 only has R2 and G2, which means it is missing a blue ring and is not complete. Therefore, only rods 0 and 1 meet the criteria, resulting in an output of 2. The constraints of the problem clarify that the string will always have an even length, each rod can only be identified by digits 0 through 9, and there will never be more than 10 rods involved. To better understand the problem, let's discuss a few edge cases. First, consider the minimum input size. If the input is R0, there is only one ring on one rod, so it is impossible to form a complete rod. The output in this case would be 0. Similarly, if the input is R0 G1 B2, each rod only contains one ring of a specific color, and no rod has all three colors. Again, the output is 0. On the other hand, if the input is R0 G0 B0 R1 G1 B1 R2 G2 B2, every rod 0, 1, and 2 contains all three colors. This means all rods are complete, and the output is 3. These examples highlight the importance of carefully analyzing the rings and rods to determine which ones meet the problem's requirements. To start, let's consider a brute force approach to solving this problem. The basic idea here is to iterate through all the rods, which are indexed from 0 to 9, and check whether each rod has all three ring colors, red, green, and blue. To do this, we would go through the ring string and count how often each color appears for a specific rod. If we find that all three colors are present, we increment our count of valid rods. The steps are straightforward. We maintain a mapping for each rod to track its associated colors, iterate through the string to update this mapping, and finally check which rods have all three colors. While this approach is simple, it does involve nested iterations, which can make it less efficient as the string size grows. In terms of complexity, the time complexity is O(n), since we process the string length n for each of the 10 rods, and the space complexity is O(1), as we only need storage for the 10 rods regardless of input size. Now, we can optimize this process to avoid redundant iterations and improve efficiency. Instead of checking each rod individually and iterating over the string multiple times, we can build a single mapping of rods to their associated colors in just one pass through the ring string. This approach takes advantage of the fact that each rod can have at most 3 unique colors, red, green, and blue. By reducing the problem to a single pass, we eliminate unnecessary repetition. Here's how it works. We use a dictionary, or an array, to map each rod to a set that tracks its colors. As we traverse the ring string in pairs, we extract the color and rod from each pair and update the corresponding set for that rod. At the end, we simply count how many rods have all three required colors in their sets. This method is highly efficient, with a time complexity of O(n) due to the single traversal, and a space complexity of O(1), since we only store information for the 10 rods. The optimized approach is the strategy we chose for this problem because it balances efficiency and simplicity. The key insight was realizing that we could process the ring string in just one pass while maintaining a mapping of rods to their associated colors. This eliminates the need for redundant iterations and keeps the solution clean and concise. Using sets to track colors for each rod is particularly elegant, as it makes it easy to check whether all 3 colors are present. When considering trade-offs, the brute force approach, while easy to understand, is less efficient for larger inputs due to redundant processing. An alternative approach using bit masking could reduce memory usage slightly by representing colors as bits and applying bitwise operations. However, this adds unnecessary complexity given the small number of rods and colors. Ultimately, the optimized approach is the best choice here, offering a blend of simplicity, efficiency, and readability while fully addressing the problem's constraints. The string rings is a sequence where each pair of characters represents a ring and its corresponding rod. The first character in the pair indicates the ring's color red, R, green, G, or blue, B, while the second character specifies the rod number, ranging from 0 to 9. For example, if the string is R0G0B0R1G1, it means that rod 0 has rings of all 3 colors red, green, and blue, while rod 1 has only red and green rings. To efficiently track this information, we use a dictionary where each key represents a rod, and the value is a set of colors that have been added to that rod. To tackle this problem, we begin by understanding the input and parsing it systematically. This approach ensures we can track unique colors for each rod without duplications, laying the groundwork for determining how many rods have all 3 colors. Now, we populate the dictionary to map rods to the colors of the rings placed on them. By iterating through the ring string in steps of 2, we process each ring rod pair. For each pair, we extract the color and the rod number, converting the latter to an integer. The color is then added to the set corresponding to the rod in our dictionary. For example, given the input rings equals R0G0B0R1G1, rod 0 will have the set R, G, B after processing, while rod 1 will have R, G. This way, the dictionary efficiently tracks the state of each rod, ensuring that duplicate colors do not inflate the data unnecessarily. Once the dictionary is populated, the next step is to count the rods that have all 3 colors. To do this, we initialize a counter at 0 and iterate through the sets of colors in the dictionary. For each set, we check if it contains all 3 colors red, green, and blue. If the condition is met, we increment the counter. At the end of this process, the counter will hold the total number of rods that have rings of all 3 colors. Finally, we return this count as the result, which directly answers the problem's requirement. The efficiency of this solution stems from the choice of data structures and its handling of edge cases. Using a dictionary that maps rods to sets of colors allows us to efficiently insert and check for unique colors. For example, a dictionary might look like this: 0, R, G, B, 1, R, G. As for edge cases, if the input string is empty, the output is 0 since no rods have any rings. When a rod lacks all 3 colors, the result remains 0. Similarly, duplicate rings of the same color do not impact the outcome because sets automatically handle duplicates. Additionally, if the string length is odd, indicating an unbalanced input, it can be flagged as invalid during pre-processing to ensure robust handling. The algorithm also boasts an optimal complexity. In terms of time complexity, processing the string rings takes O(n), where n is the string's length, since we iterate through it in steps of 2. Checking each rod for the presence of all 3 colors is O(1) per rod, as there are only 10 rods in total. Consequently, the overall time complexity is O(n). For space complexity, the dictionary has at most 10 keys, 1 for each rod, and each key maps to a set containing up to 3 elements, R, G, and B. This results in a constant space usage, O(1), since the maximum number of rods is fixed at 10. These efficiencies make the solution scalable and highly suitable for the problem constraints. The pseudocode for this algorithm further clarifies its simplicity. We initialize a dictionary where each rod maps to an empty set. Then, as we process the input string in pairs, we add each color to the corresponding rod set. Finally, we iterate over the dictionary to count the rods that contain all three colors using a subset check. If the set R, G, B is a subset of a rod's colors, we increment the count. The count is returned as the solution. This structured approach ensures clarity and correctness, solving the problem efficiently while handling edge cases seamlessly. This Python implementation solves the LeetCode problem rings and rods efficiently using a dictionary-based approach. Here's the breakdown of the code. 1. Dictionary initialization. A dictionary named rods is created where each key represents a rod, 0 through 9, and the value is an empty set. This set will hold the unique colors, R, G, B, for each rod. 2. Input parsing. The ring string is processed in pairs of characters. The first character in each pair corresponds to the ring's color, and the second character corresponds to the rod number. These are extracted and added to the corresponding rods set in the rods dictionary. 3. Color tracking. The use of sets ensures that duplicate colors on the same rod are automatically ignored, simplifying the logic for identifying rods with all three colors. 4. Counting valid rods. After processing the string, the code iterates over the values in the rods dictionary. A rod is considered valid if its set contains all three colors, R, G, and B, which is checked by verifying if the set's length is exactly 3. 5. Result return. The final count of rods with all three colors is returned as the result. This approach is computationally efficient, as it processes the input string in O(n) time and uses a fixed amount of storage for the rods, 10 sets. Edge cases such as an empty string, rods with fewer than 3 colors, or repeated colors on a rod are handled naturally by the logic. This ensures correctness for all valid inputs. Here, we start by importing the necessary libraries and defining our solution class. The goal is to determine how many rods have all three colors, red, green, and blue. To achieve this, we use a hash map where the keys are the rods, represented as characters from 0 to 9. And the values are sets that store the colors associated with each rod. We initialize the map by assigning an empty hash set to each rod. Next, we process the input string, rings, in pairs. Each pair consists of a color and a rod number. For every pair, the color is added to the corresponding rod set in the map. This ensures that we track all unique colors for each rod efficiently. By leveraging the hash set, we avoid duplicate entries for the same color on a rod. Finally, we iterate through the map's values, which are the sets of colors for each rod, and count how many of them contain all three colors, red, green, and blue. This is determined by checking if the size of the set is exactly 3. If it is, we increment our count. Once the loop is complete, we return the count as the result. This implementation is efficient and concise, relying on the properties of hash maps and hash sets to track and evaluate the colors for each rod in an organized manner. To solve this problem, we start by initializing a dictionary called rods. This dictionary will have keys as rod indices, ranging from 0 to 9, and the corresponding values will be empty sets. Each set will store the colors of rings associated with that rod. Next, we process the input string rings, which is structured in pairs, where each pair consists of a color and a rod index. As we iterate through the input, we add the given color to the appropriate rod set. For example, the first pair is B0, meaning we add the color B to the set of rod 0. Then, the next pair are 0 adds R to the same set, so now rod 0 contains both B and R. This process continues as we iterate through the string, updating the sets accordingly. Continuing with the input string, the next pair is G0, which adds the color G to the set for rod 0, making it contain all three colors, B, R, and G. Moving to the next rod, the pair R9 tells us to add R to rod 9. After that, G9 adds G, and finally, B9 adds B to rod 9, so rod 9 now also contains all three colors. Once the input has been fully processed, we move on to counting how many rods have all three colors. By checking the sets, we see that both rod 0 and rod 9 meet the condition, so we increment our count for each of these rods. After iterating through all the rods, the final count of rods that contain all three colors is determined to be 2. Thus, the output for this example is 2. Now, let's analyze another example to further illustrate how this approach works. Here, the input ring string is R0G0B1. As before, we initialize the rods dictionary with empty sets for each rod. Moving on to process the string, the first pair are 0 adds R to rod 0. Then, G0 adds G to the same rod. So far, rod 0 contains R and G. Next, the pair B1 adds the color B to rod 1. At this point, rod 0 contains the colors R and G, while rod 1 contains only B. When we count valid rods, we see that neither rod has all three colors. Rod 0 is missing B and rod 1 is missing R and G. As a result, the final count of rods with all three colors is 0. Therefore, the output for this example is 0. Let's now look at a third example to further solidify our understanding of the solution. In this example, the input ring string is R0G0B0R1G1B1. Once again, we start by initializing the rod's dictionary with empty sets for each rod. As we process the input string, the first pair R0 adds R to rod 0. Then, G0 adds G, followed by B0 adding B, so rod 0 now contains B, R, and G. Moving to rod 1, the pair R1 adds R, G1 adds G, and B1 adds B, making rod 1 also contain all three colors, B, R, and G. Finally, when we count the valid rods, we see that both rod 0 and rod 1 contain all three colors. Therefore, the final count is 2. As a result, the output for this example is 2. This concludes the walkthrough of the solution, where we processed the input string step by step, updated the rod's dictionary, and counted the rods that met the criteria of having all three colors. To analyze the time complexity of the solution, let's break it down into its components. First, we initialize the rod's dictionary with 10 keys, each representing a rod from 0 to 9. Since the number of rods is fixed, this initialization takes constant time, 1. Next, we process the ring string. The string is iterated in steps of 2 because each pair of characters represents a color and a rod. If the length of the string is n, the loop runs n/2 iterations. For each iteration, we retrieve the current rod in color, which are 1 operations, and then add the color to the corresponding rod set. The add operation for sets has an average time complexity of 1. Therefore, processing the ring string has a time complexity of n, making it the dominant term so far. After processing the string, we count the rods that have all three colors. This involves iterating over the values of the rod's dictionary. Since the dictionary always has 10 keys, this step involves a fixed number of iterations. For each rod, we simply check if its set contains exactly 3 elements, which is again an 1 operation. As there are only 10 rods, this entire step takes 10, which simplifies to 1. Combining all the steps, the dominant term remains n from processing the ring string. Thus, the overall time complexity of the solution is n. Shifting to space complexity, the rod's dictionary is the main data structure used. It contains 10 keys, each associated with a set that can hold up to 3 colors. This means the dictionary holds a maximum of 30 elements, which is constant, making its space complexity 1. In addition to the dictionary, the input string rings is provided as part of the problem and does not require extra space allocation. Beyond that, the algorithm doesn't create any other significant data structures. Variables such as color, rod, and count are used temporarily and occupy constant space. This means the overall space complexity of the solution is 1. Comparing this with a naive approach, one might iterate over all 10 rods and then scan the ring string to count colors for each rod. This nested iteration would result in a time complexity of 10*n, which simplifies to n. However, this naive approach involves redundant work and is less efficient in practice. The current solution avoids this by associating rods with their colors directly in a dictionary, processing the string in a single pass, and then performing a fixed number of checks for the rods. This makes it both clean and optimal, achieving n time in 1 space. Now, let's examine the best, average, and worst-case scenarios for the algorithm. In the best case, the ring string is empty. The algorithm simply initializes the dictionary and checks the rods, which requires constant time, 1. For the average case, where the input contains n characters, the algorithm processes all characters, resulting in n time. Similarly, in the worst case, the input still has n characters, and the algorithm processes every one of them, so the time complexity remains n. Across all these cases, the space complexity consistently stays at 1, since the number of rods is fixed and no additional memory-consuming structures are used. This ensures that the solution is efficient and scalable regardless of the input size. One common mistake is not handling duplicate rings on the same rod. For instance, if a red ring appears twice on a particular rod, it doesn't mean the rod has multiple red colors, it's still just red. Failing to account for this can lead to double counting or unnecessary computations. A related issue is choosing an inefficient data structure to track rings. Using a list for every rod can consume more memory and runtime than necessary. Instead, a set or bit masking can make operations like checking for all three colors much faster and more space efficient. Additionally, edge cases like having no rings at all, or all rings being the same color, are often overlooked. These scenarios are rare but critical to handle, as missing them could cause your solution to fail unexpected test cases. Finally, overcomplicating your logic with excessive if-else statements can make your code harder to maintain and more prone to errors. Using more concise approaches, such as sets or bitwise operations, can keep your solution clean and efficient. Another common pitfall is misinterpreting the problem statement itself. For example, confusing rod indexing or how ring colors are encoded can lead to a flawed solution that doesn't pass basic test cases. To avoid this, take time to thoroughly understand the input format and constraints. Now, when it comes to interview insights, problems like this often involve tracking multiple attributes, here, colors, across objects like rods. This is where tools like bit masking or set operations shine. They help you manage combinations efficiently. It's also important to strike a balance between readability and performance. If you opt for sets or dictionaries, you prioritize clarity, making your code easier to explain. On the other hand, bit masking offers better performance but can be less intuitive. Always highlight edge cases during interviews, such as no rings, all rings being the same color, or datasets with maximum constraints. Finally, remember to communicate your thought process clearly. It's better to explain your logic step by step than rush through it. This problem is also closely related to others you may encounter. For example, LeetCode 763, partition labels, involves tracking states across indices, while LeetCode 49, group anagrams, focuses on grouping objects based on shared attributes. Similarly, LeetCode 128, longest consecutive sequence, emphasizes efficient state tracking, and LeetCode 139, word break, requires breaking down a problem under constraints. Exploring these problems can deepen your understanding of related patterns. Now, for alternative approaches, bit masking is a powerful technique here. By representing red, green, and blue as individual bits in an integer, you can efficiently combine and check for all three colors using bitwise operations. This method is memory efficient and fast, but it may be tricky to implement if you're not familiar with bitwise logic. Alternatively, a set-based approach uses dictionaries with rod indices as keys and sets of colors as values. This is intuitive and easy to work with, but it uses slightly more memory compared to bit masking. Finally, there's the brute force approach. This involves iterating through all the rods and manually checking for the presence of red, green, and blue. While it's simple to implement and easy to understand, brute force becomes highly inefficient for larger inputs, especially when the number of rods or rings grows significantly. Its time complexity can reach n squared in the worst case, which is not ideal for competitive programming or real-world applications. Therefore, while brute force might work as a stepping stone to test your understanding of the problem, it's important to refine your solution using more efficient techniques like bit masking or set-based operations. This will help ensure your code is both scalable and optimal, making it a better fit for both interviews and production-grade scenarios. Great job! To recap, we broke down the rings and rods problem and solved it using a hash map approach, achieving both time and space efficiency. Remember to practice problems like these to sharpen your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!